Okay, so the first thing is what is feature selection? So when it comes to data science, in general, you'll have your data in tabular format, although that's not always the case. And this is an example. We've got a data set here where we're talking about cars. We've got make, model, year, etc. All of these blue columns. And then we've got a red column like value. And in this case, this would be a great data set for us to try and predict the value of cars based off of all of these other features. So each column here would represent a single feature, and that feature could be useful. It could be useful. We really don't know until we figure some more things out. But in general, people will have a conceptual model of what kind of features they think will be useful for whatever data science task they have. So that's feature selection, but why is it important? In general, data has been growing a lot. Here's some statistics here that I can throw at you, but essentially 90% of the data generated in human history was generated in the last 2 years, and that study was done over 2 years ago. We know that it's been growing exponentially, so it's probably even more staggering since then. There's a lot more varieties of data that you can get. Social media, browsing habits, shopping habits from internet activity, IoT, all these things. They're starting to become more and more readily available. So, with that in mind, that means a lot of companies in various industries are starting to see the availability of new or unique data that might be able to help them with their business workflows. The other thing is, companies are catching on. They're realizing that their data is valuable. And, before they might have signed contracts with third-party vendors to help them with some kind of workflow in return for that vendor to have their data. But, they're starting to rewrite these contracts and realize, hey, like the data that we have is also an asset that we can put to use. However, they're also realizing we have all this data, but we're not realizing the potential of it. So there's this ongoing shift in data strategy. The current business problem has been how do we acquire more data? Where can we get data, and what kind of data can we get to more comprehensively cover whatever business problems we're facing? However, a lot of companies are hitting this point where they do have data. They've set up a data lake. They have various sources coming in or streaming in. And now the problem that they face is how do we best utilize this data? They could take the raw data and throw it in, but there are better ways to go about it that will yield better results. And that's feature selection here. So I'm going to talk a little bit about feature engineering and feature selection. In data science, we have I guess like a saying that says garbage in, garbage out. What it means is, if you put data that is low quality or not very comprehensive into your model, then the predictions that are coming out of your model are also going to be low quality and not very comprehensive, right? And so quality and comprehensiveness are actually two of the most influential factors to success. When you just try to throw all the raw data that you have at a problem, you won't have the best results. You'll see this a lot on like data science competitions and Kaggle competitions. If you could simply have an amazing algorithm and raw data and throw the data at the problem, then you should have theoretically all of these people who are winning these competitions who are all getting about the same score or performance in their models. However, when you look at who has the best result, generally they will have done some feature selection and feature engineering to pass that data in a better comprehensiveness and better quality to the model so that the model outputs better predictions. So I'm going to set up an example scenario here for you. Let's pretend you're a car insurance company and you want to predict the expected amount of loss that you'd be paying out for a policy each year. This means, how much money theoretically over the course of a policy's lifetime you're paying out in claims divided by the number of years that policy has been in effect. And this helps you better price your premiums. If your premiums are lower than this expected amount of loss, then you're paying out more money on the claims than you're making. And if you price your premium higher, then you'll be making money. However, the higher you price your premiums, the less competitive your policy product is. So in our minds, we have some ideas for relevant variables, right? Year, make, model of the car, that's probably important. Safety features sound pretty important. Passive safety features like the structural integrity of the car and how reinforced the A bar is, etc. active safety features, this includes like lane steering assistance, smart cruise control, that sort of thing. Driver history, how good is the driver? And also, how well do they drive? You see that a lot these days. That's an example of IoT where, for example, a lot of insurance companies now have this opportunity for you to download an app, and then the app will use its accelerometers and geographic location information to determine your driving habits. And then lastly, something like driver location, like your zip code or something, depending on where you are, if it's a metro area or rural area, that can also be really important. Well, if we talk about feature selection, there's some obstacles, right? If you select too few features for your model, you may not give enough signal for your model to reach an acceptable performance, or you might introduce bias and draw wrongful conclusions. So here's a real life example. Let's say we only pass a very few amount of features into our model because we want to keep our model simple and understandable. So we pass in driver information and safety features. We hypothesize that safety features are really important for our model. And the result is that our model finds a trend and a pattern, and it predicts that there are going to be higher losses on cars with better safety features. This isn't a really good conclusion, right? We would expect that safety features are bad, and we should prioritize covering safe cars. Like the wrong conclusion here from the model is that we should be avoiding these safety features, when really in our minds we understand that no, safety features are good. So why does the model predict it in this way? It's because you didn't have enough comprehensiveness in your data. You introduced a bias here. So in reality, cars that have safety features, they're more expensive in general than cars that don't have safety features, because the cars that don't have safety features are a little older. And so when you have a policy that's covering a car with safety features, it's most likely a newer car and therefore more expensive. So when it gets into an accident, you have to pay more on a loss. So in reality, if you passed in the value of the car or the age of the car, your model would predict a different pattern. And that pattern would be that safety features are good. Between two cars that have the same value the same year, but one has safety features and the other one doesn't, the one that has safety features results in lower losses. Right? And that sort of thing is an example of bias, right? When you're missing the whole picture and the model is missing the whole picture, you come to the wrong conclusions. So this is one of the obstacles if you select too few features for your model. Alternatively, if you select too many features, you could bury your model in too much noise, and it fails to capture the signal you want. In general, whatever data science model algorithm you have, the way that it varies the predictions is some function of the variance and decision space in your data set that you're passing in for training. So the more that you pass in, the more it is able to nimbly move around in its prediction space. But that also means that it is more likely to fail to pick up the actual signal that you want. Also, your model can just become very needlessly complicated. In general, in data science, what we want to do is keep our model as simple as possible while still being effective. And then lastly, you increase the chances that the model catches irrelevant bias. And when I say irrelevant bias, I mean, your data isn't always going to be 100% comprehensive. And so if your data has a bias, then that bias will become more and more apparent the more bad quality data you pass in. And so when you're passing in a very large amount of features, you either have to spend the time vetting every single feature as well as the relationships between the different features, or you might end up with some kind of irrelevant bias. So here's an example. Let's say you pass all the raw data you have available and you've built a decent model for predicting car loss for policies. When you pass this model to production, you'll find that when people apply for an insurance policy and they try to get a quote online, they don't have all of this information available. And so your model will, be confused because, man, it's always seen this feature and now it doesn't see it anymore. And you've never vetted those results. So your model routinely outputs bad predictions. It's just not ready to be in a flexible production environment. In terms of irrelevant bias, here's a great example. Let's say this model starts pricing its premiums for data scientists incredibly high. And you realize that in your historical database for car losses, your company's insurance data only has one or two policies where the person or the driver listed has a profession as data scientist, and they just happen to be terrible drivers, but it has nothing to do with their profession. And so what happens is these are the only examples that your model has of data scientists, and your model will drive up the predictions unrealistically. That's an example of irrelevant bias. It's inevitable that whatever data set you have is not going to be 100% comprehensive. And because of that, if without artful selection of your features, you're forcing yourself to either have a lot more work on your plate for your model to be effective, or you face the risk of something like this, catching relevant bias. Another obstacle in feature selection is a lack of feature engineering. And so when I talk about feature engineering, all I'm simply saying is, let's say you have a given feature or a couple features. You can use those features and combine them in some way, shape, or form to generate another feature. A simple example might be, instead of giving a model income, you give it income squared, right? Or you have income as an interaction with, I don't know, age, right? When you're passing in this new feature, it's not really new. It's just an old feature that's been transformed. So here's another real world example. If we pass in raw latitude and longitude coordinates into a model that's used to predict Airbnb rental prices, we'll find that in general, most model algorithms will not have the complexity and the ability to be able to discern any valuable information from the latitudes and longitudes. And so the incorrect conclusion here would be that latitudes and longitudes are not valuable features for our model. In reality, though, they are. You just need to do some feature engineering. In this case, you could do some geospatial work and generate new features where you draw a radius around each latitude and longitude coordinate, find all of the other listings that are within that radius, and average the price of those listings, or just count up the number of listings within that radius. These new features that we've engineered, technically, they're just using other features that we have already, but we're combining them in such a way that it's easier for the model to pick up the concept that we're trying to pass. In this case, the concept that we're trying to pass is, what is a competition in the area? Because that competition is likely going to determine or have a we gave a quick overview of feature selection, what it is, why it's important, and some of the obstacles that you might face. Next, I'm going to talk about some of the common feature selection techniques that I've run to during my time as a data scientist. I'll give some pros and cons, and then lastly, we'll talk about one of our methods that we use here at Quantico. So before I go into it, just a disclaimer, given enough time, human-led feature engineering and feature selection will be better than automated feature selection. But in many of the use cases that we run into, our man hours are much more valuable than our machine hours. And also, machines can do simple things much faster than humans, so it may be more efficient. So here are some of the feature selection techniques that I'm going to talk about today. Some of these might look familiar to you. You might have seen it in a statistics course or something like that. So I'll try and touch on these briefly, but feel free to ask any questions about these as well. So you may have heard of correlation matrices. Essentially, you'll just calculate a correlation matrix for all of your data, features, and targets. And then features that are correlated with your target are kept, and features that are highly correlated with one another, you'll remove all of them except for the one that has the best correlation with the target. That way you help remove some collinearity in your model. And then everything else is removed. It's very quick. It's very simple. There's a couple downsides. First of all, correlation matrices are only effective with continuous variables. So you limit yourself greatly in terms of the kinds of features you can even select. Second of all, it doesn't capture any nonlinear relationships. So you're only capturing variables that are able to draw a straight line with your target. And also, even though you're dealing with a little bit of the collinearity problem, you're not really capturing multivariate collinearity well. So in conclusion, it's fast, it's simple, but it's a little lacking. Here's another example of something that I've seen. It's called backward stepwise regression. So if you've ever run a linear regression model, you know that you get a couple of statistical values out of your model. You get some measure of magnitude of your effect or pattern that you're seeing. That's the coefficient that's boxed on the left in the image. Then you have some function of spread or statistical noise representation. And that's your standard error, t-statistic, p-value, 90% confidence interval. They're all very related. In this case, I'm just going to focus on the p-value. The p-value here gives a probability of significance based off of the spread or the distribution in the data. And so the higher the p-value, the more likely that whatever pattern you're seeing is just noise and it's not actually a real pattern. So that's why you'll see in a lot of studies and research papers, you'll see something like, oh, this is statistically significant. The p-value was less than 0.05. That means, in more simplistic terms, the probability that whatever effect we're seeing here is not real is less than 5%. So we're pretty confident that this is a real effect that we're seeing in our data. So what backward stepwise regression does is it takes advantage of this measure of significance or spread. And what you'll do is you'll run your regression model with all of your features and your target. And then you'll look at your p-values and say, hey, which one is the most likely to be noise or the least significant? And then you'll remove that feature. Then you'll run the model again, and you'll repeat, and you rinse repeat over and over again until however many features you want. I'm going to be honest, I've seen this a lot. It's very widely used, but it's very not supported in the statistical world. In terms of how linear regressions work and the assumptions that they're based off of, you break a lot of the assumptions. You break least squares theory. So, you're looking at the data multiple times. That's determining whatever your final model is. So, you're biasing your final model based off of your observance of the data already. Also, you have some degrees of freedom issues, and it doesn't account for collinearity at all. If you have two variables that are very collinear, both of them are going to be considered not significant, when in reality, one or the other could be significant. And so what happens is your model may oversimplify, or essentially it's kind of like a greedy search algorithm that's faulty, and it won't really reach an optimal conclusion. So it's not great. But the advantage is it's fast, it's easy. So in reality, what's really stopping companies from using it aside from academia telling them, hey, this isn't good? Not much. So that's backward stepwise regression. There's also another variant called forward stepwise regression, where instead you start with one or two variables, and then you add each variable iteratively and see which one is best. And then you keep that one in the model and you continue. It's essentially the same thing, but in reverse. So a more statistically valid alternative that's been presented to me from statisticians would be to run variable permutation models. It's a way to help maintain some of your assumptions that you would normally keep statistically. So when you train your baseline model, you use that as just a baseline, I guess, where you look at the performance of your model. Then for each feature, you reshuffle the feature's values. So in this case, in this image, I'm shuffling miles per gallon. So, maybe there's a car that had really good miles per gallon, but we're now going to take all of the miles per gallon that we've observed and we just redistribute them randomly amongst all the cars. So now that car that used to have really good miles per gallon, it'll look like it doesn't have good miles per gallon or, some other thing. It's very random. What this does is it preserves the variable's distribution. However, you lose the connection that that variable has with actual observations. So you're essentially removing any signal that miles per gallon may have given previously. So then, once you reshuffle that feature, you just rerun the model and compare the difference in model performance. Once you repeat this for every variable, you'll see which variable is most or least valuable in that iteration, right? So in this example, we shuffled miles per gallon. There's two outcomes here that we could face, right? If we rerun the model with this shuffled miles per gallon, and the model still performs just as well as it did before, it's telling us that miles per gallon really was not that valuable. On the other hand, if we shuffle miles per gallon, and then when we run this model, the model performs very badly. That's telling us that miles per gallon is a very important very important feature for our model. Some minor issues here. One, you have to run a lot of different iterations of models, more so than something like backward stepwise regression if you want to also, kind of permutate downwards. Another issue is that if you have features that are correlated, they're both going to be inflated in their importances. But I think that's you're going to see these pros and cons for most of these feature selection techniques. So many of you might be familiar with lasso regression. It's a regularized version of a GLM, of a generalized linear model. So when I say regularized, what I mean is we're trying to pare down the complexity that the model can be, and we establish some sort of penalty. In this case, the penalty is very simple. When you add up all the coefficients that you have in your model, which represents the complexity of the model, that is your penalty. So whenever the model wants to assign a greater weight or greater effect to a feature, it has to weigh between increasing the performance of the model and decreasing the penalty. And so as a result, specifically with lasso regression, the general behavior that this model will have is it'll penalize some features to 0 and then increase other features more. And what that means is the model views certain features as not being worth enough to add value to the coefficient because the penalty outweighs that value. So, you might start with 10 features, you establish a lasso regression with a penalty, and once you run the model, you'll find, 3 or 4 of them are dropped. Again, this is determined by your penalty that you assign, but this is something that you can apply not just with lasso regression, but with a lot of different regularization methods. But this is just one example. And so whatever coefficients were set to 0, those are the features that we remove, and the rest are the ones that we select. Now, if you're using something like a tree-based method, this is a decision tree or random forest. You might have also heard of XGBoost. These are methods where you try to split the observations or the data based on the features provided. And so when you split on these features, for example, back to the example that we had of car values, the model might at first say, hey, let's try to split on miles per gallon, and anything greater than a certain value of miles per gallon is in one bucket, and anything less than that is in another bucket. Then it'll evaluate, hey, how much did that contribute to the predictive power of the model? In other words, were the two buckets very different now in terms of the car values that are within them? And so it'll keep repeating that until some parameter that you set. And so after you have this model that you've completed, you can evaluate the importance of each feature by looking at how often that feature is used for splitting, as well as how much it contributed to your predictive power. In a regression, it would be how much it was able to account for variance. In a classification task, it might be something like a impurity score, like a Gini, a weighted Gini or something. It's very fast. It's very easy. And a lot of people use this too. I would be more comfortable using something like feature importances from a tree-based method. But there are some downsides. So one, it biases the importance of variables with a large decision space. So what I mean by that is, since the model is trying to split values based off of some determined amount, if you have one feature that is just the number of doors on a car, right? It's not a very large decision space. You could have 2 doors, you could have 4 doors. Maybe in very, very uncommon circumstances, it could have 6 or more. So when the model tries to split, it doesn't really have that much room to work with. So it's only going to split it so many times. However, if you have another feature that's like the length of the car in centimeters, right? This is a very large continuous variable. And the model will have many different opportunities to split that feature, and therefore it might use it more often. So that's what I mean when I say if there's a feature that has a large decision space, then the tree-based method might use it more often, which will inflate its importance in the feature importances calculation. Lastly, I just want to cover something really quick. This is called principal component analysis. It's normally used as a dimensionality reduction technique, but I have also seen in some cases that people will use it to calculate feature importance. So principal components analysis tries to remap your variables using some differential equations, calculating the null space and eigenvectors. And when it does this calculation, it's trying to maximize or preserve as much variance in the data set as possible. And so your first component will will capture the dimension that still has the most variance. Then the second component will capture the second best representation of variance. And all of these components will not have any correlation to each other. So some people have used this as a way to look at feature selection. What they'll do is they'll ask, hey, how much does each feature weigh into the first, second, and maybe third component in a PCA algorithm output? What this means is how important is a variable in determining the variance that's captured in the data set. So while that might be a good way to start, there is a big assumption here. PCA is an unsupervised algorithm, so it's not looking at your target. It's not really looking at the relationship between your features and your target variable, which, for our car model example would be a car value. Instead, it's just looking at variance. And so there's a very big assumption here that the features with the most variance are the most important, which is not always the case. But this is still something that I've seen done. So that's a quick review of some common feature selection techniques. Next, I'm going to jump into a case study. This is one of our business scenarios and the automated feature selection technique that we came up with. So this is our business scenario. One of our products, we provide well log characterization. We'll take drilling data, gamma logs from a well, and we'll train a model on those with the target being, sonics and densities, formation evaluation logs. These are rock properties. And so after we've trained this model, then when someone drills a new well, we can take the EDR data and the gamma log data that they've done, or we can take it in real time. We'll pass it to the same model, and it'll output the sonics and densities for them. And this, unlocks a lot of potential because you can look at the VPS ratios. You can calculate a lot of other rock properties that are derivatives based off of density and sonics. You just understand more about the rock. So in this environment or in this scenario, we have a couple of characteristics. So one is we regularly build localized models, and there are two reasons for that. One is, as the slide says, there are data quality issues. From project to project, from client to client, some features, they don't stay as important from one project to another. This is because, when they're drilling, maybe they're using a different rig, the measurement tool is faulty, the operator is using it in a different way, or it's offset to a different degree. We have ways to help remedy some of this, but the reality is a lot of the times the data situation that we have from project to project can vary greatly. The second reason why we might build localized models is because the geology varies a lot based off of, obviously where you're drilling. You might not want to use a model that's been trained on Permian unconventional wells for, something that's conventional or offshore, much farther away. So we need to build these localized models relatively quickly and still have to deal with the variance that we see from circumstance to circumstance of how powerful our features are. One other sort of, requirement or characteristic of the scenario is we need to build models that are performant and not interpretive. What I mean by that is we just need models that give good results based off of our historical information. We don't need to understand how they're calculating, sonics and densities in this case. And so with this scenario in mind, this is the way that we do automated feature selection. We have this process that we call exhaustive input sensitivity analysis. It's kind of similar to some of the techniques that I had given earlier, but it has our own spin, and we do a couple things to kind of address some of the disadvantages or downsides that we've dealt with. So let's say we have 36 features in our model. We'll train individual neural networks on feature subsets. So if it was 36 features, we'll have 36 models, each trained on 35 features. They just each drop out a different one. We'll partition the data very heavily, and we'll actually train several neural networks within that same feature subset, but using different data partitions for training, testing, validation, etc. Then we'll look at the average or overall model performance for each feature subset, and then we'll drop whatever feature that model dropped. Then we'll continue on for the next iteration. And we keep all of the best models of every iteration until we have some kind of threshold minimum input that we give, and that's when the process stops. So that was kind of, I can understand that this might be a little complicated, so I broke it down a little bit more. Here's a very basic example. We've got a simple data set where we've got 3 features, A, B, and C. We're trying to predict D. And we can partition the data as many ways as we want, but essentially it's subsets of the data themselves, not subsets of the features. So now we will subset this partition data where we drop one feature each time. So we've got one that's AB, one that's AC, and one that's BC. You'll notice that each of them, they've dropped one feature. Then for each of these feature subsets, we'll train several networks using the different partitions for different portions of our data science workflow. This gives us a little bit better understanding of the overall performance for that feature subset because the models aren't looking at the entirety of the data every time. Then we calculate the overall performance of our models for a given feature subset, and then we compare the performance between subsets. So, in this case, let's say our bottom feature subset, A, C, D, happens to yield overall models with the best performance. Then we'll move on to our next iteration where we've decided we're going to drop B, and we'll continue. In this case, there's only 2 features left, so there's not much more we can do. Here's a real life example. I took a plot. This is a plot that shows our drop sequence when we run through exhaustive input sensitivity analysis. In this case, from 0 to 36, these are the features that our data set started off with. And the y-axis represents how long that feature lasted in our drop sequence. So the bars that are really short represent features that were not very valuable to our model, and therefore they dropped it. And the ones that are very tall are features that continued on through the algorithm through each step. And so therefore they're very valuable because the model drops in performance when they don't use it anymore. Another way to look at this is to look at the performance of each model as we continue to drop features. So you can look here that on the x-axis, we see the number of inputs for our best iteration model. And then on the y-axis, we have our normalized performance, or RMSE, or normalized error. A couple things to notice. This performance is not monotonic, although we would like it to be as close to monotonic as possible. So what we're looking for is a smooth performance transition from a really low error to a really high error. If that's not there, if we see just the performance jumping up and down a lot, we have to really look into whether or not the data is good enough quality or if we're missing something else in the equation. Also, we're using multiple neural networks for each iteration. If you train 2 neural networks on the same data, but you don't set your randomization seed properly, then your results might be slightly different because of the randomly initialized weights when you start training your model. And so by using these data partitions, we are less dependent on that initial random weights that we have. It also allows us to remove a degree of statistical bias because we're not using the entire data set every time like we would in something like backward stepwise regression. One more characteristic of this I guess, workflow that we have is we generate a very large model base. We essentially have the best combination of features at each number of features level and the best model for that level. So this gives us a lot of flexibility for construction and evaluation of our models' performances, as well as ensembling our models. You know, I don't think we'll have time to talk about ensembling as much in this case, but essentially we are able to combine these models to hopefully give even better performance. And we have a special way of doing that too. And so since we want to combine a lot of models, and that's sort of our standard workflow, we would like to have an initial workflow that generates a lot of models, and this one does that. There's a couple pros and cons here, right? So the pros, which I'll talk about first, collinearity isn't really a factor because feature selection is just a result of model performance. And that model performance is measured based off of how well the model generalizes to the holdout data, which it hasn't seen. Also, we get the best models at each permutation level. I mentioned that previously, which gives us more flexibility in production. As an example, you know, let's say we're running this model in real time for a client and their resistivity tool goes dark. We could either keep running that same model, or we can just ask, hey, within our model base, which models did we have that were our best models that did not use resistivity? If we dropped resistivity, you know, somewhere in the middle or early on, then chances are we have a lot of models that wouldn't really care about resistivity at all. So there are some cons as well. You know, this is not some sort of silver bullet that solves feature selection for everyone. You know, neural networks are more complex and less explainable. So if I was trying to do some sort of analysis that presented something to clients to help them understand the nature of the data, neural networks are not the way to go. Something like the linear regression or decision tree model. There are plenty of other models that have more explainability. Second of all, you know, if you haven't really already figured it out, we're training a ton of neural networks on large feature sets, and the larger the feature set gets, there's a geometric progression, I think, of the number of neural networks that we're training. So, you know, if our feature sets start growing to 50, 60, 100, this will start to become very computationally expensive. So it's a good idea, you know, to optimize your neural network architectures in this case and parallelize what you can. So as an example, when we train our subset features for a given level, we can train all those neural networks in parallel, and that'll speed up the process greatly. So in conclusion, this is what we kind of covered in the webinar. We talked about feature selection, what it is, why it's important, some common feature selection techniques that I've seen in various industries, and then the one that works for us for one of our workflows. And then now we're going to enter a time of Q&A. So feel free to ask questions in the chat, and you know, we'll tackle them now. Also, this is my email, etin@quanticoenergy.com. If you have any questions that you think you thought about later, or you're too nervous to talk about it right now with an audience here, feel free to shoot me an email instead, and we can talk about it more in depth. But otherwise, that's it for the webinar. Thank you.
Excellent. Thank you so much, Edward, and thank you everybody for joining us today. Like Edward said, we're about to jump into a bit of a Q&A, so go ahead and type out your questions into the chat. I received a couple questions throughout the webinar directly to me, so I'll go ahead and read those off in a minute. Before I do that, I have a couple announcements on behalf of Quantico. One of them is we recently had a paper accepted through the ARMA conference. Although that won't be happening in person this year, our paper will be available soon through OnePetro, and it basically covers machine learning based seismic inversions and earth modeling. So it's one bit of news. And in other news, we also recently received the HGS Corporate Star Award for 2019 to 2020. So it's very exciting for us here at Quantico. And in addition to that, we're also launching not only a new website, but a brand new logo that really resonates with the direction of our company going forward to take an even more digital approach to the oil field. And we're always coming out with a lot of great content. And a part of that is our webinars, but also written articles by our subject matter experts. So if you're interested in any of what I just mentioned, make sure you follow us on LinkedIn so that you can keep track of the latest and greatest here at Quantico. So one of the questions that I received during the webinar was for you, Edward. What are some key telling signs that would tell you that you haven't done enough feature engineering when you're looking at the results of a model?
That's a great question. That's something that a lot of data science departments struggle with. I don't think there's a surefire way of knowing whether or not you've hit some sort of global optimum on your model performance. But in general, what I've seen is people will continue to look at their features and feature engineering if their model isn't performing well enough for whatever business case scenario they're looking at. At the end of the day, how well your model performs is actually not the most important thing in data science, although it does feel like it sometimes. And it's very easy to latch on and tunnel vision to like, oh yes, our model performance is this number and we need to hit this threshold. In reality, how you're using that model in production is way more important. As an example, in my previous position at an insurance company, when we're applying models, for example, we have a model that looks at claims information and tries to determine the probability that a claim is fraudulent. And the accuracy is not that great. It's slightly better than random guessing. But the important thing here is that we have specialized, we have claim specialists that were trained specifically to look for fraudulent claims. And the problem was they were getting an overflow of thousands of claims. They have hundreds that they have to deal with every day. They have to prioritize them. So the purpose of the model was simply to say, hey, these look suspicious based off of things that you've generally flagged as suspicious. And therefore, let me just take away some of the time that it takes to shuffle through all these claims and show only the ones, or prioritize or order or rank the ones that you want to tackle first based off of the probability of the fraudulence as well as the level of impact if you do resolve it, right? And so in this case, even though the model doesn't perform that well, it performs well enough for its intended function, and therefore that's all you really need. So in this case, I guess I don't really have a tangible answer for you here, but in general, people will continue to focus on feature selection and feature engineering until their model is good enough for whatever its intended purpose is.
Thank you, Edward. I hope that answered your question. So the second question that I received was, how important is domain knowledge to feature engineering? Are there workarounds for non-subject matter experts when it comes to feature engineering?
That is also a great question. I would say domain knowledge is very important for feature engineering. If you're just given a bunch of columns with numbers and you don't know what they mean, how are you supposed to know how they interact or what kinds of concepts you're trying to represent or how they even relate to the target? So, something that one of my mentors have said to me in the past is domain knowledge is like data science gold. So whenever you're working with clients and customers, ask as many questions as you can to try and understand more about how the data is being represented, the step-by-step workflow from the creation or inception of that data to when it reaches your table, when it reaches your data frame. All of these things are really important. Now, that being said, you also asked whether or not there's workarounds for lack of domain knowledge. And that is also a good question. I have seen responses. So, you've seen a lot of driverless AI companies out there. These are companies that are trying to provide a way for you to run a data science workflow without having any data science experience. Part of that is also to enable data scientists to work without any domain knowledge. Essentially, it's a combination of feature selection and feature engineering in a most brute force method. So let's say you're given a data set, you don't have any names for the columns, you're trying to do some feature engineering. Some methods that I've seen in the past is they'll generate an insane amount of engineered features. They'll take every column and multiply it by every other column. They'll find ratios. They'll run principal components analysis. Then look at the weights and then generate interactions between them. There's a lot of different ways that you can, engineer several features to create a new one. And what they'll look at is after they create all of these features, they'll look at how much more variance they've created and how much of that variance is correlated with the target. And then lastly, they'll run some of these feature selection techniques that we gave in the past that I just touched on in the webinar. So essentially, they'll sort of shotgun all of these different engineered features based off the initial raw data set. And then afterwards, they'll hope that some of them stick through the feature selection process. That's the extent of what I've seen in terms of trying to feature engineer without any domain knowledge. Although in reality, most data scientists, when they're working on data, they tend to have at least some conceptual understanding of what that data is. So, even if you have a little bit of domain knowledge, you should be able to understand which feature engineering routes make more sense and which make less sense.